Our second example, this is actually the only other example we will do, is of this style. So you'll get these two different styles in your homework. Um, about half of them, or maybe more than half of them, are vertical plates submerged in a fluid. And a few more look like this. So this one says, find the fluid force on the end of this gasoline tank. Gasoline is 749 kilograms per meter cubed, and gravity is 9.8 meters per second squared. So here's the idea. So they're showing us this, very large cylindrical tank filled with gasoline. I guess you imagine this on the back of a truck, or maybe that's underground, like at a gas station. And so here it's not that fluid force is around the plate and pushing in on the plate. No, the fluid is inside the tank and it's pushing against the end. So inside there, the gasoline presses outwards. You almost might think at first like, well, if it's inside, then maybe the plate, like the end of it doesn't experience any pressure. But no, right? It's pushing. It's trying to push out. At every that's point. And the deeper you get, right, the more pressure there is. The higher up, the less pressure. Okay, that's kind of Pascal's principle kind of coming into play here a little bit. Okay. Now, another big difference, and why I chose this example for us here, is the end of that tank is circular. And that can, there's a different way I would recommend approaching a circular plate, either whether it's submerged or if it's like a tank in this case. We're going to have to set up an XY plane again. But when it comes to anything that's circular, I recommend setting up a little bit differently. So here's what I've got, and you can see some of my work there as well. If it's circular, I find much easier just to set it up in the traditional way, right? So put the center of that circle at the origin and just go ahead and make your X and your Y the traditional setup, right? So positive X this way and positive Y that way. You can certainly not take my advice. You could still make positive Y going down. You might kind of like that. Um, I do recommend, though, that you make the center of the tank at the origin, right? If we did it in a way that was consistent to the way we did the previous example, right? The the fluid level is the top of the tank, right? It's completely filled. So, would you want to make your x-axis, going through that point at the top? You could, but just for the way the equations are going to come out, I recommend you don't. Okay, so let's pick it up from here. If we were to draw L of y, and well, you see my work for L of y there already. But let's take it from the top. So what is L of y, right? That is usually the most difficult thing to figure out. Here, L of y, well, it's always a vertical, or excuse me, oh, it's always a horizontal line, a horizontal length, like so, and it would go all the way across. We're always going to get L of y from an equation, right? So before, we had to figure out the equation of that line that described like that edge of the tank at an angle, or the edge of the plate at an angle. This time, the equation is the equation of the circle that we're looking at. So we've done this a couple times by now. The equation of this circle, and this is where it's really helpful to put the center at the origin. The equation of that circle is x squared plus y squared equals 4. Okay. And just like in the previous problem, we want to solve this for x. Okay, so solving for x, subtract the y squared, take a square root 4 minus y squared. And you notice I've got this note there. When we take that square root, right, we should put a plus or minus in front, but we don't. We only consider the positive part. But when we only consider the positive square root, that means it's the right half. We're only looking at this right half of that circle. If we were to have solved for y in a similar way, that would be the top half. But since we solve for x, obviously that's describing a horizontal, okay, you get it, left and right. So the negative would be the left half. The positive version is the right half of the tank. Now that's really important because you notice L of y goes all the way across. So if this only describes the right half, it's only describing this right here. But L of y is the whole thing. So we need to multiply that by 2. So L of y equals 2 times the square root of 4 minus y squared. Okay, it's kind of like a symmetry thing happening, right? So we just do half of it and then double. All right. We also want to know d of y. So for d of y, in a sense, I think it is helpful to, kind of draw the surface level. Obviously it's not going across, right? It's just at the very top, but I think that's helpful. So d of y is going to come straight down to where we drew our length. So there's, it's kind of tough to fit it in there. Okay, there's d of y. You get it. Now when it comes to d of y, because of the way we've set up our x and y axes, we want to be careful. So the way we set it up in the previous problem, it was very simple. D of y was just y. That's not the case here. Let's look at this very carefully. What is that length there coming down from 2 to wherever we drew our line? Okay. So it turns out if y is going positive in this direction, then the length y would be here. So I'm trying to do a little dotted line. Let's zoom in on this. This will be better. Try and focus. Okay, so this little length is y, coming up off the y-axis. That's the same as the way it was in the previous problem. It was just pointed down. So if that's y, this little length is y, then what is this length here? And well, you would think if this is 2, right, the total length is 2, and this is y, then the part that's remaining that we want is 2 minus y. Take the total length and subtract that part, and you'll get what's left. So in this problem, and I've got it off here on the side, d of y equals 2 minus y. Now I've got to check for L of y, but it occurs to me, you can check d of y as well, and I think that makes sense here. I didn't write it on the page, but okay, let's check d of y. Hey, when we're at the very top at 2, what is the depth of the gasoline when you're at the very top? It's 0, right? Well, when you plug in 2 here, do you get 0? Well, yeah. Hey, what is, if you're on the x-axis, what is the depth? Well, if you're on the x-axis, the depth is 2, and that's y equals 0. So if you were to plug in 0, would you get a depth of 2? Okay, yeah, you would. Hey, what if you're at the very bottom at -2? What's the depth? Well, it'd be 4. And if I plug in -2, yes, I indeed get a depth of 4. So that's helpful, and we can check L of y in the same way. I think that's probably a good idea. So kind of those three positions make sense here. So at 2, if you're at the very top, what is the length? Well, the length is 0, right? Hey, if you plug in 2, do you really get 0? Well, yeah, 4 minus 4. Hey, if you're on the x-axis, what is the length? All right, well, this is a circle, so the length there is 4. Hey, if you plug in 0, do you really get 4? Well, yeah, because 0 square root of 4 times 2, yep. And if you're at the very bottom, what is the length? Well, from the drawing, the length is 0. Hey, if I plug -2 in, does it really give me 0? Sure does. And so those will really confirm that we did this correctly. Or you might even catch, that you should have multiplied by 2 and you never did, like if you made a mistake of doubling somewhere. Okay, great. So we've got L of y, we've got D of y. Let's set up, I'll try and keep this handy for us as I show you the integral. There it is. Okay, so this time fluid force equals, and they told us in the problem that gasoline is 749 kilograms per meter cubed, and we're going to multiply that by gravity, so times 9.8. Okay, notice the limits of our integral from -2 to 2, right? Well, we're thinking the y values, all right? Now it turns out that -2 to 2, it's almost like we're starting at the deepest and then ending at the shallowest, which seems to be backwards. Like, shouldn't we begin at the shallow and end with the deep? Turns out it doesn't matter because all we're doing is adding up all of those little length times depths. So it doesn't matter if we start from the top and go down or if we start at the bottom and go up. And really, it just depends on the way you set up your drawing in the first place. What you do want to be sure, though, when you set up your integral, it's from least to greatest, -2 to +2. Okay. And then from there, well, we've got d and we've got L dy. Okay. You know what? Let's point out one thing. As we talk about symmetry and stuff and taking advantage of symmetry, do you think it would be possible, just looking at our drawing and thinking about the context, we go from -2 to 2, right? Do you think it would be possible to go from 0 to 2 in our integral and then double? Could we go 0 to 2 and then double it? Would that be okay here? It seems at first like that would be fine and that might make our work easier, but turns out we cannot do that in this case. Why not? If you go from 0 to 2, then you're looking at just the top half of the tank. But the pressure on the top half of the tank is not the same as the pressure in the bottom half of the tank, because the pressure down here, because it's further down, the bottom half of the tank experiences a lot more pressure than the top half. So we have to go from -2 to 2. Although the doubling that we see back here with this 2 is a left-right doubling. When we have this 2, essentially what we're doing is calculating the pressure on the right half and then doubling it to get the left half, and that's fine. That we can do. Okay, that's good. Always be on the lookout for symmetry, but only where it's appropriate, of course. All right, let's go ahead and knock out this integral right here. This one's got a little bit harder. let's simplify as much as we can. So multiply these. Let's bring that 2 out as well. So we got fluid force equals 14,680.4. Integral from -2 to 2. 2 minus y, square root 4 minus y squared dy. Okay. And you might be wondering, what are we going to do with this integral? Turns out the best way to approach this is to distribute your square root and actually create two separate integrals. And I'll show you that right here. So we'll keep that constant out. Multiplying by 2. Subtract, multiplying by y. Okay. And each of these integrals will need a different approach. And it'd be a lot more interesting if we were in class together and I could say, how might we go about this integral? How might we go about this one? Turns out this is going to be the more difficult one. This one is a bit more straightforward. I'll show you the approaches. So here on the left, well, that 2 is not really doing anything. It's just the square root of 4 minus y squared, right? So that's going to have to be a trig sub. However, over here, when we've got a y, the way that all fits together, we can do a u substitution. Okay, let's knock this out. Let's begin with that trig sub. I'm going to go through this pretty fast. Not lightning fast, but, we've done plenty of these. Okay, so looking at that first integral here, well, we can pull the 2 out, of course. Ignore this work. We'll come back to that. Then we think, okay, I see my square root. Let's set up our triangle. So setting it up, that's the square root piece has to be on a leg, which makes that a 2 and a y. And so I'll just show you all this. We notice we should use sine. Sine is the square root over 2. So 2 sine theta equals that square root. Here we can use a cosine. Cosine y. Cosine of theta is y over 2. So we could say 2 cosine theta equals y. The only reason we need that y is so we can get dy, which here is -2 sine theta d theta, dy. Okay, so putting these into our integral, there's the 2 in front, from -2 to 2, 2 sine theta times -2 sine theta d theta. And okay, pull of our constants out, make it sine squared. And we're hopefully in familiar territory. We're going to use a trig identity on sine squared theta, and that's where we pick it up. Let's see if we can fit it all. That's where we pick it up right here. So sine squared theta is 1 minus cosine 2 theta over 2. Bring that 2 out to make a -4, and then let's just go for the antiderivatives right now. So we got theta, and for cosine 2 theta, that would be 1/2 sine 2 theta. Recognize that sine 2 theta is 2 sine theta cos theta. So the 2 and the half cancel, so we get this line here. And of course, we got to convert the thetas back to y's. So using 2 cosine theta equals y, dividing by 2, inverse cosine, so that's inverse cosine y over 2. Sine theta times cos theta, looking back to the triangle. I'll let you guys do that. If you want to, it works out as this, y times square root 4 minus y squared over 4. And then we're evaluating from -2 to 2. When you're doing these problems in the homework, or if you saw something like this on a test or a quiz, the expectation is that you would do it, using all the steps of, say, a trig substitution in this case, as opposed to a table of integrals. And it's good practice. You want to practice those integration techniques. I know it's like that table of integrals is right there, and could we just look at a table of integrals to do that? Well, we could, but unless it's specified in the problem to do that, um, then you'll need to do it the long way because we need to refine those skills as well. Okay, so at this point, when we plug in our 2 and our -2, some nice things happen. So, inverse cosine of 1 turns out to be 0, and plugging the 2 in here gives you a 0 as well. Plugging in -2, now inverse cosine of -1 is pi, but you'd get the 0 again there. So this whole thing works out to be 4 pi. Keep in mind that's only the first integral. That's this part. We still have to do this one. So let's check that out. Okay, we've got a u sub. Right, u equals 4 minus y squared. And we're just going to, I might not even read line by line. There's our du, and then isolating the y dy, putting it all in there. Okay. U to the 1/2, yeah. Okay, antiderivative 2/3 u to the 3/2. Put your u back in, 4 minus y squared to the 3/2. And now even here still, plugging in the 2 and the -2, what happens, right? So plugging in the 2 gives you 0. Plugging in the -2 gives you 0. That whole thing, that whole integral right there is simply 0. And that allows us to get our answer. So fluid force putting both those values of those integrals back, it's 14,680.4 multiplied by 4 pi minus 0. And here, two ways you could answer, depending on your preference. A lot of people in this sort of a case prefer to just leave the pi in the answer. Makes sense. And leave it as 58,721.6 pi newtons. Other people, you're like, well, if we're using a decimal, I mean, why not just multiply the pi in? And if you did that, it would be 184,479. And I rounded to 2 decimal places, 0.35 newtons. Either way, perfectly fine with me. Okay, so just a few closing words on these concepts. So again, there's kind of these two major types of problems you'll see. So you'll see vertical plates, like in our first example. If you see a vertical plate, my recommendation, there's multiple ways to do this. Maybe you prefer something else, but my recommendation would be make that x-axis the surface of your fluid, and strategically place your y-axis. So here it made sense to go right down along that edge. Okay. In other problems, it might make sense just the way it's based on the shape of your plate. So in other problems, it might make sense to go right down through the center of the plate, and maybe you get some nice symmetry doing that. But here, and in a lot of problems you'll just go right down along that edge. And I recommend make your y, going positive, in the downwards direction, since depth does that. That matches how depth works. Okay. And then to find L of y, that's the harder one. You're going to have to base it on some sort of equation. So get the equation here, solve it for x. The other type of problem you'll see are these tank problems. And it'll be find the force on the end of the tank. All right. So in that case, you're thinking the surface of the fluid is at the top of the tank. Now here we happen to have a circle. And whenever you have a circle, whichever type of problem you're looking at, if it's a circle, I recommend just drawing it out in the traditional way. Make the center of that circle at the origin. And here, I thought it was fine. Just, put the y going upwards. You could certainly have y going down there. That's there's no issue with that. But that said, I find when you're putting a circle and the center's at the origin, just make your y going up, because I think it just gets a bit overwhelming even if you put your y going downwards. In that case, it's a little bit too much to think through. Okay, that's my advice. Go check out the homework.